To find the antiderivative of the cube of the cotangent, first you want to split the cube into the square of the cotangent multiplied by the cotangent, right? Because there are powers of 2 and then there's a power of 1 here, right? Together the powers will add up to give you the original power of 3. Next thing you want to do, you want to express this squared of cotangent as cosecant square x minus 1. Right? Because this comes from the identity that you should recognize. Cotangent squared is equal to cosecant squared minus 1. Now, obviously you're gonna distribute, right? You're gonna distribute the cotangent to each of these two terms to give you precisely these two integrals, right? And we're splitting the difference into two separate integrals, right, to make it easier to work with one individual integral without any complications, right? So the two products will give you each product will give you a single integral that you're going to work with, right? So the first product is the cotangent times the cosecant squared, as you see here, and the second one, the second distribution, is the cotangent times the -1, which gives you the minus of the antiderivative of the cotangent. Okay, so the next thing you want to do, you want to use U substitution precisely for the first integral. And the U substitution is that this cotangent x is going to be the U, right? So we're going to indicate this as a U, right? And this will be negative du, obviously, right? Because the du here is the negative cosecant squared, right? So the negative du is precisely this part here. Notice that if you negate the du, you're going to have a minus du. This part becomes positive, cosecant squared x dx, right? This is precisely what we have here, right? So if we go back, once again, you will see that this is a minus du, which is equal to positive cosecant square x dx, right? You can see from the algebraic manipulation that this is indeed true, right? So the next part is that we write the first integral using the U substitution, right? We took out the negative du, we took out the negative sign outside the integral here, so as a result we have minus integral u du for this first integral. Now the second integral, realize that you can write the cotangent as the cosine divided by the sine, right? That should be clear. Basically it's the reciprocal of the tangent function, right? So the next part is going to be using another substitution for this integral, for the second integral, right? And that's going to be v is going to be sine x, right? So the general rule of thumb is when you see a fraction of two functions, the bottom fraction, the bottom function, the bottom in the denominator will be the v variable, the new v substitution here, right? So we're assigning the sine x as the v, right? And the dv is going to be cosine, which is great. That's exactly what you have in there. Cosine x dx is the dv. Right, so next what you're going to see, first we're going to solve the first integral. We know that the antiderivative of the u is 1/2 u squared, right? But there was a minus sign, so the minus kept. And the second part is the integral of 1 over v dv, right? Because we used another substitution, v was equal to sine x and dv is equal to cosine x, right? So we substitute everything in terms of v. Right? And you see a plus sign. What is that plus sign? The plus sign means that we're going to have a constant, right? This constant came from this first antiderivative that we found, right? Because every antiderivative has a constant. If you forget it, you will get a point deduction in your test or your homework assignment, whatever it is that you're going to do, right? So don't forget the constant, right? We didn't find the second antiderivative yet, right? So this constant is from the first antiderivative that we found. So now we're expressing the first antiderivative in terms of the x variable, right? Because the x variable is the original variable, right? What was the u? The u was cotangent of x, right? So u squared is cotangent squared of x, precisely, right? So we substitute this first term in terms of x. We express it in terms of x. Now the second integral here gives us its own antiderivative. We know that the antiderivative of 1 over v is exactly ln of absolute value of v. Absolute value must be used because the inputs of the ln's of the logarithm can never be negative, right? It must be positive, right? So there will be absolute value bars like this. So this integral, the antiderivative for the second integral, becomes minus ln of absolute value v. Now you notice, why is it plus c now? Why is it plus c? There was a k before. Well, guess what? There's another antiderivative we just found. It has its own arbitrary constant, right? That constant added with the original constant k from the first antiderivative gives us a third constant c, right? So add this constant k with the constant generated by the second antiderivative gives us the third constant, which we wrote as plus c, and that's going to be the final constant. That's why I wrote it with a letter that you very well know as part of your final answer, right? Plus c. But we're not done yet. The last step is to make sure that the v here variable is expressed in terms of the original variable x again. We know that the v is equal to sine x, right? So it makes sense that the final answer is going to be minus 1 half cotangent square x minus ln of absolute value of the sine of x, right? Because v is equal to sine x, right? Based on our original substitution, plus the constant, right? So this is indeed your final answer, and if you got this answer, it means you did correct work. Everything is great. Thanks so much for watching. See you in the next video.